Lesson 5.1 is about the real number system. Our learning target, we are going to differentiate between rational and irrational numbers and approximate the square root of an irrational number. Remember that square root symbol looks like this, just as a review. And if I asked you what is the inverse of square root, you should be thinking squaring a number, okay? Opposite operations, just as a little review. All right. The real number system. Guys, you've seen this graphic before. It's in our classrooms. You've seen it in textbooks. You may have seen it on some important tests. But the real number system is whole numbers, okay, like 0, 1, 2, 3, and so on. After whole numbers, we were introduced to integers. Okay, what are integers? Negative are whole numbers and their opposites. So examples, -5 and 5. -3 is an integer, 2 is an integer. So any whole number and its opposite. Is 5 also a whole number? Absolutely. Okay, so 5 is an integer, 5 would be best classified as a whole number, but it's also an integer. -5 would be best classified probably as an integer, okay? And then we have our rational numbers, which we've been talking about the past few days in class. Our rational numbers. So write down some examples of some rational numbers. I'm going to put 0.6 repeating. That's our bar notation we talked about. You could put 3/5, a fraction. A ratio of two integers is a rational number. You could put a terminating decimal, a decimal that ends. That's also a rational number. Okay, all of these numbers, rational numbers, integers, whole numbers, they are all part of the real number system. Any whole number, just to clarify, because I got this question, any whole number, can it be written as a fraction? So take 3, for instance. 3 can be written as 3/1. So 3 is a whole number. It is also an integer. It is also a rational number. Okay, what we're going to talk about today is irrational numbers. So, if rational numbers are decimals that either terminate, stop, or they're decimals that repeat, irrational numbers are numbers that don't repeat and they go on forever and ever and ever. And the best example would be pi. Okay, pi is that 3.14 and the decimal continues forever, 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 and it never ever repeats. Also, the square root of 2 is an irrational number. Okay, it goes on forever and ever and it never repeats. So within the real number system, we have both rational and irrational numbers. All right, and we want to be able to be given a number and determine what kind of number is it. All right, so that's the goal. Let's go ahead and write a definition for irrational numbers. So we have it in our notes. Please remember, if you're thinking of questions as we're doing this, write them down on the left side, highlight, so we can get them clarified in class. We're going to be working tomorrow on classifying numbers, rational versus irrational, so we'll have a chance to really practice. So irrational numbers are numbers that go on forever and never, ever, ever repeat. Okay, so I told you that pi is probably the most common example, but a lot of times we use 3.14 for pi, okay? That is not exactly pi. So I just want to bring this to your attention. Pi is actually a decimal that continues forever and ever and ever and doesn't repeat. We use 3.14 because it's a number that's a lot easier to work with, and we can actually work with it rather than the exact pi. So when you see 3.14, that's actually a rational number. That decimal stops, it terminates. The pi symbol represents a number that goes on for forever and ever and ever and ever and doesn't repeat. So that is irrational. Okay, I just want you to see the difference. All right, so let's do an example here. If I said name the irrational, and I give you 12 and 89/100ths, the square root of 12, and 12 over 44. Okay, we're gonna identify the irrational, and let's justify our answer. So 12 and 89/100ths. This is a decimal. It terminates, it stops. So we learned yesterday that decimals that terminate are rational numbers. So that's not irrational. Square root of 12, let's think. Is that a perfect square? Well, 3 times 3 is 9. 4 times 4 is 16. That's not a perfect square. Off the top of our head, we don't know what that exact number is. So we could get out our calculator. Okay, so let's kind of box this one and we'll move on to the next one. 12 over 44, that's a fraction. Is it simplified? No. Do I need to simplify it? Not necessarily. We can, and it'd be 6, because we can divide 2, over 22. Now that's simplified. But again, we learned yesterday, this is a ratio of two integers. It's a fraction. Whoops. So this is also a rational number. Okay? So the square root of 12, even if I was at home and I didn't have the graphing calculator to really look and see what the square root of 12 was, I know that this is my irrational. Okay? It's not a perfect square, and if I actually did the math, I would find that that was a decimal that goes on forever and ever and doesn't repeat. Okay, so rational versus irrational. Now, when working with the square root of irrational numbers, for instance, like the square root of 12, we can approximate and come up with something that will be pretty close. So let me show you what I mean. If I said the square root of 18, is this a perfect square? So guys, think about, well, 3 times 3 is 9, that's not close. 4 times 4 is 16, that's pretty close. So I could say 4 times 4 is 16, or you could say the square root of 16 is 4. Well, the square root of 16, that's close to 18, but it's not exact. 5 times 5 is 25. So you could say that the square root of 25 is 5. All right? So the square root of 18 has to be between the square root of 11 and the square root of 25, in between 4 and 5. So if I wanted to plot this on a number line, here's 4 and here's 5, I know that the square root of 16 is 4, the square root of 25 is 5, So where would I put the square root of 18? Is 18 closer to that 16 or 25? Well, 18 is closer to 16, so I'm going to put the square root of 18 right here. Okay, so I'm just approximating. Again, I don't know exactly. So we could say that the square root of 18 is between 4 and 5. Okay, we don't know for sure. We're approximating. It's between 4 and 5. Now, what if I asked you, would 4.9 be a reasonable approximation of the square root of 18? Well, is 4.9 on the number line? 4.9 would be over here closer to 5. So looking at the work I've done, is that reasonable? No, because 4.9 is closer to 5, and I know that the square root of 18 here, it's going to be over here closer to the square root of 16. So an approximation would be closer to 4. So maybe 4.1 even, or 4.2. Okay? So again, we're just approximating. All right, so you need to think about the perfect squares up here and work with the numbers that you know. And then that'll help you out to figure out where the square root of 18 would lie between. Okay, so we'll work on this more in class tomorrow. Again, we differentiated between rational and irrational numbers, and we're approximating the square root of irrational numbers on a number line. So, if just in case, the assignment that we're going to be working on in class tomorrow is page 67, 1 through 18. So if you want to start looking at it, get a head start, you're more than welcome to. But we'll spend some time doing this in class tomorrow.